There is too much information in the world about any subject. Too much. So that important pieces could be lost. Browsing the web could take ages with little results. In recent years, artificial intelligence taking a big step. With that progress came a flood of new books, algorithms, open software, open data, tutorials and courses for anybody to follow. Instead of this, we might be enjoying beautiful summer sun, go hiking on a mountain or play with kids. As a group of EAGE members, we want to help geoscientists identify the pieces of information relevant to them by contributing to the monthly AI newsletter. We also don't want to overwhelm you. The newsletter is brief and to the point, with links to relevant information and quick overview and opinions from us. Google just released a network that achieves breakthrough performance on natural language processing, reasoning, and code generation tasks. It is called PaLM. It is a large transformer-type neural network developed using pathways, which, by the way, have 3 times more parameters than GPT-3 model. So what Pathways' idea anyway? Pathways' idea is to use one machine learning model for several tasks. It is like reusing part of your code that you already written for your new project. The benefits include faster learning, and it can be done for any input data type, like text, image, and others. So it's very promising technology for geoscience applications. If you want to learn more, there is a good paper that accompanied that research, as well as some folks have replicated the architecture and published on GitHub account. There is a tool that can create complex 3D geological models of folded structures, fault networks, and unconformities with underlying stochastic approach that is essential for handling and analysis of uncertainty. The developers of that tool did not want to pick a fight with the well-known commercial packages, but rather collaborate as a community to push development of innovative geomodeling methodologies. The German RWTH Aachen University developed fully open-source 3D structural geological modeling toolbox, GemPy. I've prepared another video for you where you'll learn how to start working with GemPy and how to build your first geological model with it. Here it is. The book mostly focuses on practical and implementational aspects, keeping the theory part is limited to what is necessary for understanding supervised and unsupervised machine learning methods. The book starts with identification of problem statements within the oil and gas cycle that can be used as a good candidate for improving workflow efficiency or accuracy. Several real industry applications examples are presented there. Plus, there is overview of Python syntax and functionalities that goes with those examples, so that you can learn Python programming within the oil and gas context. There is a One O'Reilly series, a comprehensive textbook on practical machine learning covering the fundamentals, neural networks, deep learning, and several advanced topics in comprehensive detail. And before you jump on it, some basic understanding of underlying math like linear algebra, calculus, and some proficiency in Python are prerequisite. This book is well suited for those who already know what machine learning is, and as a reference materials for more advanced users. The researcher at this paper proposes to improve machine learning and deep learning algorithms for well-log interpretation by integrating parameterized quantum circuit. And the idea behind that is that the quantum circuit, or quantum computing as a whole, can bring greater generalization potential for machine learning and deep learning models. The authors tested the presented quantum technique on well-logs from real-field data, and to show the difference between the model, they compared the results with the deep learning-based architectures like CNN and LSTM. They found that with fewer training examples, the quantum-based approach performs better than the others. Moreover, the authors emphasize that the quantum technique is suitable when working with thin lithology layers. That is a challenge for other models. And you know what? I've gathered the important information about quantum computers to learn from, and reviewed the paper in my other video for you in here. Hyperspectral imaging is a remote sensing technology that splits the image up to many virtually
non-overlapping, very narrow bandwidth. Such spectrally detailed data can contain a lot of information on the actual materials and elements whose spectra are mixed with each other. For example, general RGB, not hyperspectral image, contains pixels that can represent many spectral signatures mixed together. That is why much remote sensing analysis is done to unmix those mixtures. Can you guess what type of network is used here again? You probably guessed it right. It is transformers. But in this case, plus convolutional autoencoder. The relevance of this case for geoscience is twofold: spectral unmixing of field dataset and hyperspectral imaging itself, which can be used for remote sensing of geological outcrops. More interesting topics have been covered in my previous newsletters as well. I've created a playlist for you with all the releases. Check them out if you haven't already.